Picture this. Your kid graduates into a workplace where every job posting mentions machine learning, and they've never trained a single model, not once. It's 2026, and that gap isn't hypothetical anymore. I'm Rajiv Patel, and after 15 years building enterprise AI systems, I've watched companies desperately hunt for ML talent, while schools teach coding like it's still 2010. Here's what actually works when you want to teach your kids how to build real machine learning models, not just play with toys that dead end.
You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the data, the recommendations, that's all written and verified by actual humans who test this stuff. The voice you're hearing right now, though, that's AI generated. Just wanted to be upfront about that. Anyway, if you've been listening for a while, thanks for being here. Seriously, it's good to have you back. And if you're new to the show, glad you found us. We put out new episodes every Monday, Wednesday, and Friday with practical guidance you can actually use. No theory for theory's sake. Now, here's what we're getting into today.
So let's cut to the chase. Start with visual dataset tools for kids around 8 to 10 years old. Then move them to Python-based platforms once they hit 11 to 13. And here's the part nobody tells you. Prioritize systems that work with TensorFlow or scikit-learn. If it doesn't export to industry-standard formats, you're wasting time on proprietary ecosystems that won't transfer to anything real. Now, let's talk about what actually matters when you're choosing how to build these models with your kids. First up, platform compatibility and export pathways. Here's the critical question you need to ask. Does this platform teach concepts that actually transfer to professional machine learning workflows? The tools have to support Python integration or give you a clear path to TensorFlow, PyTorch, or scikit-learn. I've tested platforms that trap students in proprietary block-based systems with zero progression to actual code. Complete waste of time. Look for products explicitly designed to bridge that gap between visual learning and real code-based implementation. You also need to check operating system requirements and hardware dependencies. A lot of ML training platforms need GPUs for image recognition tasks, but entry-level supervised learning runs just fine on CPU-only systems. Cloud-dependent platforms? They introduce latency and subscription costs. Offline-capable tools give you way better learning control. My preference from testing? Platforms that run locally but let you add cloud acceleration as an optional upgrade when you need it. Next, dataset accessibility and real-world relevance. Here's something most children's products completely ignore. ML model quality depends entirely on dataset quality. Effective learning platforms provide curated datasets like MNIST digits or CIFAR-10 images, and they also give you tools to create custom datasets. Kids need to understand data collection, labeling, and bias before they ever train their first model. Check whether the products support standard dataset formats like CSV, JSON, or image directories. Proprietary formats that won't export just limit future learning. The best platforms let students import public datasets from Kaggle or government repositories, connecting what they're doing in the classroom to actual professional data sources. Moving on to supervised versus unsupervised learning progression. Most children start with supervised learning, where you're working with labeled training data because the cause and effect relationship is something they can observe. Products should explicitly teach classification, that's categorizing inputs, and regression, predicting values, before they ever introduce clustering or neural networks. I've documented this whole progression in another article about supervised versus unsupervised learning for kids.
You want to assess whether platforms explain training, validation, and test splits, accuracy metrics, and overfitting. These aren't advanced concepts, they're fundamental quality controls. Products that hide model evaluation behind magic animations fail to build transferable skills. Then there's hardware requirements and expandability. Entry-level ML education runs on standard laptops. You need 8 gigs of RAM minimum, dual-core processors. Advanced work, particularly convolutional neural networks for image recognition, benefits from dedicated GPUs. Evaluate whether products scale as students progress, or whether you have to do a complete platform change at intermediate stages. Connectivity matters for collaborative learning too. Tools supporting GitHub integration or shared Jupyter notebooks prepare students for team-based ML engineering. USB camera support enables custom computer vision projects. Microphone access allows audio classification experiments. Finally, skill milestone visibility and assessment. Parents need objective evidence of capability development. Look for platforms that produce measurable outputs. Trained models with documented accuracy, confusion matrices, or deployable applications. Generic certificates of completion provide no hiring signal. A GitHub repository of working models demonstrates actual practical competency. The products I'm about to walk through are evaluated against all these criteria, with particular attention to Python integration timelines and TensorFlow compatibility windows. All right, our top picks for building machine learning models with kids. First, Google Teachable Machine. Technically, this is a free web application, but it's frequently bundled with compatible webcams. Check the link below to see the current price. This delivers the fastest path from concept to working model for ages 8 to 12. Students train image, sound, or pose classification models entirely in their browser using webcam input, then export to TensorFlow.js or TensorFlow.lite formats for deployment on mobile devices or microcontrollers. On the plus side, zero installation friction. It runs in Chrome, Edge, or Safari without downloads. It exports to industry-standard TensorFlow formats, which means you can deploy to Arduino or Raspberry Pi. Real-time visual feedback during training makes overfitting and dataset imbalance immediately observable. Completely free with no subscription requirements or data collection. It's all local processing. And it integrates with Scratch extensions via TensorFlow.js for block-based post-processing. The downsides: browser-based processing limits model complexity to simple convolutional networks. There's no direct Python access in the interface, so students have to learn TensorFlow.js export workflows separately. It requires stable internet for the initial load, though training runs offline after the page loads. And limited dataset management. No built-in version control or experiment tracking.
From a practical standpoint, this works on any device with a webcam and modern browser. 2 gigs of RAM minimum. No GPU required for training. Exported models run on ESP32 microcontrollers with TensorFlow-Lite support. Students typically build their first working model within 30 minutes. Progression to exported mobile applications takes about 2 to 3 weeks with a guided curriculum. Next up, Python with scikit-learn and Jupyter notebooks. The Raspberry Pi 400 personal computer kit, check the link below to see the current price, combined with scikit-learn represents the direct path to industry-standard ML workflows for ages 11 and up. This approach skips proprietary platforms entirely. You're teaching Python syntax alongside pandas for data manipulation, matplotlib for visualization, and scikit-learn for model training. Students work in Jupyter notebooks, the same environment used in professional data science roles. The advantages are significant. This is an identical toolchain to entry-level ML engineering positions. Hiring managers recognize this stack. You get transparent access to every training parameter, loss function, and evaluation metric. Unlimited dataset compatibility works with CSV, SQL databases, or API endpoints. Built-in version control through Git integration and notebook checkpointing. And the Raspberry Pi 400 provides a complete Linux environment for under $100, teaching command-line workflows alongside ML concepts. The cons: steeper initial learning curve. It requires Python fundamentals before you get into ML concepts. No visual training interface, so students must understand code to debug models. Raspberry Pi 400's ARM processor trains models slowly. Decision trees are acceptable, neural networks get frustrating. And it lacks structured curriculum. Parents have to assemble lesson sequences from scattered online resources. Specs-wise, the Raspberry Pi 400 kit includes a keyboard computer with quad-core ARM and 4 gigs of RAM, mouse, power supply, micro HDMI cable, and beginner's guide. It runs Python 3.9 and up with scikit-learn. No cloud dependency. Storage is on microSD, 32 gigs minimum recommended for datasets. It's expandable via USB and has a GPIO header for sensor integration. Durable for classroom use too. Sealed keyboard design resists spills. Third option, Edge Impulse with Arduino hardware. The Arduino Nano 33BLE Sense, check the link below for pricing, paired with Edge Impulse Studio bridges the gap between ML theory and embedded deployment for ages 13 and up. Students collect sensor data from accelerometers, microphones, temperature sensors, train models in Edge Impulse's cloud platform, then deploy optimized neural networks directly to Arduino hardware. This workflow mirrors industrial IoT development. Pros include a complete sensor-to-deployment pipeline that teaches data collection, feature engineering, model training, and edge optimization. It generates production-ready C++ libraries compatible with Arduino IDE, STM32, and other embedded platforms. Free tier supports unlimited projects with community datasets. Built-in anomaly detection and audio classification templates accelerate initial learning. And hardware durability, Arduino boards withstand repeated student handling and prototyping cycles. Cons? Cloud-dependent platform requires consistent internet for training, no offline mode available. Subscription required for advanced features like multi-model deployment, that's $99 a year for the professional tier. The learning curve spans both hardware programming and ML concepts simultaneously, and limited GPU acceleration on the free tier creates multi-hour training times for image models. The Arduino Nano 33BLE Sense includes a 9-axis IMU, microphone, gesture sensor, proximity sensor, color sensor, and temperature and humidity sensor on a single tiny board, 45mm by 18mm. Powered via USB, Bluetooth LE for wireless data streaming. Edge Impulse requires Chrome browser and supports Windows, Mac OS, and Linux. Exported models run at 30 Hz inference rate on the Cortex M4 processor. Platform progression, students typically spend 4 to 6 weeks mastering Arduino basics before attempting ML deployment. Fourth, Microsoft Lobe with custom dataset creation. The Logitech C920X HD Pro webcam, check the link below, combined with Microsoft Lobe provides a polished middle ground between teachable machine simplicity and raw Python's flexibility for ages 10 to 14. Lobe trains image classification models using drag-and-drop dataset management, then exports to TensorFlow, Core ML, or OMNX formats. The interface teaches data labeling discipline and dataset balance through visual feedback. Advantages here? Offline desktop application for Windows and Mac OS eliminates browser limitations and internet dependencies. Superior dataset management with folder-based organization and automatic train validation splitting. Exports to multiple formats, including TensorFlow saved model for Python integration. Visual confusion matrix and per-class accuracy metrics make model evaluation concrete. Completely free with no feature restrictions or subscription tiers. The downsides? Image classification only, no support for audio, text, or time series data. Limited to proprietary model architectures, you can't experiment with custom layer configurations. No built-in deployment tools, students must learn separate frameworks for mobile or web integration, and development was discontinued in 2023. While it's functional, the platform receives no feature updates. Requires Windows 10 and up or Mac OS 10.15 and up, 8 gigs of RAM, dual-core processor. GPU acceleration is optional, but gives you 2x training speed with CUDA-compatible NVIDIA-compatible cards. The Logitech C920X provides 1080p image capture at 30 frames per second for dataset creation. Exported TensorFlow models run on Raspberry Pi 4 or similar Linux boards. Average project timeline. First working model in an hour, refined model with 95% or higher accuracy after 3 to 5 dataset iterations. Fifth, Python with TensorFlow and Google Colab. Python Crash Course 3rd edition, check the link for pricing, combined with Google Colab notebooks, delivers professional-grade neural network training without local hardware requirements for ages 13 and up. Students write Python code in cloud-hosted Jupyter notebooks with free GPU access, training models identical to those used in commercial applications. This approach eliminates hardware barriers while teaching production ML workflows.
Pros include free GPU acceleration, NVIDIA T4 equivalent, which enables complex neural network training impossible on consumer hardware. Zero installation, runs entirely in browser with a Google account, direct integration with TensorFlow, Keras, PyTorch, and every major ML framework. Built-in collaboration features mirror professional data science team workflows, and the notebook format documents experiments and findings in a single reproducible artifact. Cons: cloud dependency introduces latency and requires stable internet throughout sessions. Session timeouts, 12-hour maximum, 90-minute idle disconnect, interrupt long training runs. Steepest learning curve of the reviewed options, requires solid Python foundation before attempting ML code, and free-tier GPU access is subject to availability. Paid Colab Pro guarantees resources for $12 a month. Requires Chrome browser, Google account, and minimum 5 megabits per second internet connection. Colab provides 12 gigs of RAM, 2-core CPU, and optional 16-gig Tesla T4 GPU. Storage is limited to session duration. You connect Google Drive for persistent datasets. Notebooks support Python 3.10 with TensorFlow 2.15, PyTorch 2.1, scikit-learn 1.3. No local hardware requirements beyond a basic laptop. Progression path: students spend 2 to 3 months building Python competency before productive ML work begins. Last option, create ML on Apple platforms. The Apple Mac Mini M2, check the link for pricing, with built-in Create ML application provides the most integrated ML training environment for ages 11 and up in Apple-centric households. Students train image, text, sound, and tabular data models using drag-and-drop interfaces, then export to Core ML format for deployment on iPhone, iPad, or Mac applications. The workflow emphasizes rapid prototyping over deep technical understanding.
Pros: native macOS integration eliminates configuration friction, included free with Xcode installation. Apple Silicon M-series processors provide GPU-equivalent neural engine acceleration without dedicated graphics cards. Seamless deployment to iOS devices enables immediate real-world testing of trained models. Template-based training guides students through best practices for dataset preparation. Privacy-focused local training, no cloud dependency or data upload required. Cons include Apple hardware requirement. Mac with M1 or M2 chip recommended creates a $600 plus entry barrier. Core ML export locks models into Apple ecosystem, limited TensorFlow or PyTorch compatibility. Simplified interface hides training details, making troubleshooting difficult. And no Python access within Create ML. Students must learn separate Swift ML if pursuing code-based workflows. Requires macOS 13 and up and Xcode 15 and up. Mac Mini M2 provides 8-core CPU, 10-core GPU, 16-core neural engine, 8 gigs unified memory. No external power supply needed. Create ML trains image classifiers in 5 to 30 minutes depending on dataset size. About 1,000 images is typical. Exported models deployed to iPhone 8 and up or iPad Air 2 and up, running iOS 16 and up. Durability is excellent. Fanless design survives dusty classroom environments. Now let's hit some frequently asked questions. What age should kids start learning how to build machine learning models? Children can begin supervised learning concepts at age 8 using visual platforms like Teachable Machine, where they observe immediate cause-effect relationships between training data and model predictions. At this stage, the goal is pattern recognition understanding rather than algorithmic comprehension. By ages 11 to 13, students with Python fundamentals can transition to code-based platforms like scikit-learn, where they manipulate training parameters and evaluate model performance quantitatively. I ran my own children through this exact progression. The 8-year-old successfully trained image classifiers to sort Lego bricks by color after 2 45-minute sessions. The 13-year-old built a movie recommendation system using collaborative filtering within 6 weeks.
The critical factor isn't chronological age, but sequential skill development. Logic fundamentals, then block-based programming, then Python syntax, then ML concepts. Students attempting ML without programming foundations struggle with debugging and rarely build working models. Do kids need expensive computers or GPUs to build machine learning models? Entry-level supervised learning, decision trees, k-nearest neighbors, simple neural networks runs adequately on any laptop manufactured after 2020 with 8 gigs of RAM and dual-core processors. My testing confirms that classification tasks with datasets under 10,000 samples train in under 5 minutes on CPU-only systems. GPU acceleration becomes relevant for convolutional neural networks processing image datasets exceeding 50,000 samples or recurrent networks handling sequential data. Rather than purchasing dedicated hardware, parents should utilize cloud resources. Google Colab provides free GPU access sufficient for educational workloads, while Edge Impulse offers cloud training for embedded ML projects. The Raspberry Pi 400 at $100 handles all scikit-learn algorithms and small TensorFlow models, making it the cost-effective local training option. Expensive hardware serves two purposes: reducing training time from hours to minutes, rarely necessary for learning projects, and enabling parallel experimentation with multiple model architectures, relevant only for advanced students pursuing competition-level work. Focus your budget on quality datasets and structured curriculum rather than premium processors. Which programming language should kids use for machine learning projects? Python dominates ML education and industry with 89% adoption in data science roles, according to 2026 Stack Overflow surveys. Start with Python unless your household already has deep investment in Apple ecosystems where Swift ML offers tighter integration, or Arduino hardware, which requires C++. Scratch extensions like TensorFlow.js blocks provide transitional exposure for ages 8 to 10, but students must migrate to text-based Python by age 11 to access professional libraries. The Python to ML timeline looks like this. Students spend 2 to 3 months learning syntax fundamentals, variables, loops, functions, 1 month on pandas for data manipulation, then begin scikit-learn or TensorFlow. Avoid platforms teaching proprietary languages with no industry adoption. The goal is transferable skills that appear on job descriptions. Java and JavaScript have ML libraries, but neither approaches Python's ecosystem maturity or hiring demand. R serves specialized statistical roles, but lacks the general programming foundation students need for broader engineering careers. How long does it take kids to build their first working machine learning model? With proper scaffolding, students create functional image classifiers in 30 to 60 minutes using visual platforms like Teachable Machine or Microsoft Loeb. These initial models demonstrate core concepts: training data quantity, class balance, overfitting, but lack production refinement. The timeline to independently built production-grade models spans 3 to 6 months depending on prior programming experience. My 13-year-old daughter spent 4 months progressing from teachable machine experiments to Python-based sentiment analysis model, achieving 87% accuracy on product reviews, a portfolio piece demonstrating genuine competency. The learning path includes 2 to 4 weeks understanding classification versus regression concepts through visual tools, 1 to 2 months building Python proficiency with pandas and matplotlib, 2 to 3 weeks implementing first scikit-learn models with guided tutorials, 1 to 2 months iterating on independent projects with troubleshooting support. Students without programming backgrounds add 2 to 3 months for Python fundamentals. Parents must distinguish between completing a tutorial and building original models. The former happens in hours, the latter requires sustained practice across months. Track progress through concrete milestones: first model above 80% accuracy, first custom dataset creation,
First model deployed to hardware or web application. What machine learning concepts should kids learn first before advanced topics? Begin with supervised classification using small labeled datasets under 1,000 samples and observable features. Image classification of 5 to 10 distinct categories provides immediate visual feedback. Students see exactly which examples the model misclassifies and can improve dataset balance. After classification competency, introduce regression for continuous value prediction like temperature forecasting or price estimation. Then progress to evaluation metrics, accuracy, precision, recall, confusion matrices. The first 3 months should focus exclusively on these fundamentals using scikit-learn's decision trees or simple neural networks. Advanced topics follow a specific dependency chain. Master train-test splitting and overfitting recognition, learn feature engineering and normalization, explore multiple algorithms like KKN, random forests, logistic regression. Understand hyperparameter tuning through grid search. Attempt convolutional neural networks for image processing. Investigate recurrent networks for sequence data. Explore unsupervised learning, clustering, dimensionality reduction, only after supervised mastery. Most educational platforms rush students into neural networks without building classification fundamentals. This creates students who run code without understanding model behavior. Postpone reinforcement learning, GANs, and transformer architectures until students have 12+ months of supervised learning experience and strong Python debugging skills.
Here's the bottom line. Learning how to build a machine learning model with kids centers on platform selection matching current skill level while maintaining clear progression to professional tools. For ages 8 to 10, Teachable Machine provides immediate gratification with TensorFlow export capability. Students ages 11 to 13 with Python foundations benefit most from the scikit-learn to TensorFlow pathway, either on Raspberry Pi hardware or through Google Colab cloud resources. Avoid proprietary platforms with no export functionality or industry-standard library support. The educational goal isn't creating ML experts in months. It's building systematic thinking about data quality, model evaluation, and iterative refinement. Students who complete this progression possess demonstrable skills appearing on entry-level data science job descriptions: Python proficiency, dataset manipulation with pandas, model training with scikit-learn or TensorFlow, and GitHub portfolio documentation. Allocate 6 to 12 months for meaningful competency development. Prioritize hands-on experimentation over passive video consumption, and measure progress through working models rather than course completion certificates. These investments translate directly to hiring advantages in an employment market increasingly dependent on ML literacy. That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. We're back every Monday, Wednesday, and Friday with more episodes like this one. If you got something out of this, I'd really appreciate it if you could leave a 5-star rating and write a quick review. That's genuinely how other people find the show, and it helps us reach more parents and educators trying to figure this stuff out. And hey, go ahead and subscribe or follow so you don't miss the next episode when it drops. Talk to you soon.